Where I left off in the last video, we saw that if we had a magnetic field coming in from the right, and we had this loop of I guess we call it metal or a circuit, and it's carrying a current in this, where the current is coming in this direction. You could imagine positive protons, although we know the electrons go in the other direction. But if the current is coming in this direction, then going out that direction, we figured out using the right-hand rule and just this formula that the net force of the magnetic field coming in this direction on this arm of the wire or the circuit is net downwards, right? And on this arm, it was net upwards. And so it provided a net torque on this circuit, or as I said in the last video, a paperclip, and where this dotted line is the axis of rotation. And then this is how I showed you it would rotate, right? Where the magnetic field is essentially pushing up on the right-hand side and pushing down on the left-hand side. It has no effect over here on the top and the bottom. So it would rotate in this direction, and then this was kind of what it looks like after it rotates a little bit. And the whole reason why I did this, I said, well, this arm, which is the same as this arm, the net force is still upwards, out of our screen. But that upwards direction is now no longer going to be completely perpendicular to the moment arm distance. That's the moment arm distance. Now the moment arm distance is kind of coming at an angle out of the page. So only some of this net outward force from the magnetic field is going to be perpendicular to the moment arm. And so the torque on it will be less, but it's still going to be torque in that same direction, kind of coming out of the page on the right and into the page on the left. And the same is true of the left-hand side. And then you go all the way to the point that the coil is actually vertical, where this side right here is on top, and this side is on bottom, below the plane of your video screen. And at that point, the torques actually there is no net torque. And why is that? Because on this top part, when it's pointing straight out at you, when it's right here, the magnetic field, the force of it, the force that it's affecting the circuit, is pushing straight up. So there's no longer any net torque, right? Because the force is pushing straight up, and that moment arm distance, this distance, is now also pointing straight up. And torque is also a cross product, so you actually care about the perpendicular forces. So there, at this vertical point, there's no net torque, and the same is true at the bottom of the circuit, because at the bottom, the magnetic field force is going to be downwards, which is parallel with the moment arm distance, so there's no net torque. And I said, well, maybe there's a little bit of angular momentum that keeps this object rotating, and then it will rotate to, and this is where it gets interesting. I'll draw it neatly. Then it'll rotate to this point. Once again, I want to have the perspective. That's perspective. It'll rotate here. So let me just make sure I have all. So here it was rotating in this direction and in that direction, right? And then here maybe there's no longer any torque on it, but it still might on the top be moving to the left and on the bottom moving to the right, up to a point that it's going to get into this configuration where this side is, so it's rotated at this point, it has rotated more than 90 degrees. So this edge is now this edge. It had rotated from here all the way, it's still pointing out of the screen. But if this edge is the same as this edge, now the current direction is going to be like this, right? Because this edge has rotated down, so it's rotated from that position all the way to the back to this position. So the current is now coming, let me draw it on the right. The current is coming like that, like that, like that, going up here and to the right, up like that, right? So the current now on this left-hand side, although it was the former right-hand side, it's still going in that upwards direction. So when you take the cross product, what is going to be the net magnetic field on that? Or the force of the magnetic field? Well, you do this same right-hand rule, point your index finger up, put your middle finger in the direction of the magnetic field. This is the palm, this is your other two fingers. Let me draw the fingernails just so they're painted fingernails, not that mine are. Then your thumb points upwards. So on this side of the coil, we still have an upwards force. And if you do the cross product, or you do the right hand rule on the bottom side or the behind side, you could even imagine it, you're still going to have a net downward force. So now all of a sudden you can imagine the thing had rotated, so it had rotated in the way I drew it here, where it pops out on this side and it goes in on that side. And it had done it all the way to the point where we had rotated more than 90 degrees, but now all of a sudden the net force due to the magnetic field is going to reverse, right? Because the side that has a current going upwards is now the left-hand side. So now the force from the magnetic field is out on this side, and you're going to want to rotate in the opposite direction. Hopefully that makes sense. Just think about what happens. Visualize this coil rotating. So what is essentially going to happen is you're going to rotate like I did here on the top. Maybe once you get to this level, you're going to have a little bit of angular momentum that'll keep you rotating, or rotational inertia that'll keep you rotating until you're in something like this configuration. Maybe you go all the way back to this configuration where it's essentially a complete 180 degree turn, right? And then since on this side the current's going to be going up and on this side the current's going down, because you've essentially flipped this thing over, then the effect of the magnetic field is going to say, well, upwards on the left, downwards on the right, right? And so it's going to turn the other way. So if you think about it, it's going to keep oscillating. Let me draw it from a, well, I don't want to draw it from that angle because I don't want to confuse you. So we have a problem. If we wanted to turn this into some type of electric motor and keep it spinning, we would either have to reverse the current once you get into this configuration, or either turn off the magnetic field, or maybe you could reverse the magnetic field to get it going in the other direction. And actually you have another problem, which is a slightly lesser problem, is if this was a circuit and you just kept turning over and over the circuit, the wires would get twisted here, so you couldn't do it indefinitely. So the solution here is something called a commutator. A commutator. So let me draw a commutator. So what if, I have, let's see, the same circuit, which I have now drawn messier, but it has these two leads. Has these leads that essentially curve. You can imagine them curving out of the page. And then we have a circuit. You could imagine leads here too. And this round thing and this thing they're touching each other the whole time. So current could pass through it. Right? Let me draw my battery. This is positive and this is negative. So up here on the circuit, the current's always going to be flowing in this direction. It's always going to be flowing in this direction. It's always going to be flowing up and like this, right? Now, when you're in this configuration, what's going to happen? Well, the current is going to flow down here. That's going to be I, and that's going to be I. And when you do your right-hand rule, we have the same magnetic field. I haven't changed the magnetic field. It's coming in from the left. So just like we did before I cleared the screen, you use the right-hand rule and you'll figure out, well, the net force from the magnetic field is going to be upwards here and downwards here. And that's what's going to create that net torque, and you're going to rotate this part. So this part of this contraption is going to rotate. You could imagine maybe there's like a little pole here. Maybe it's a non-conducting pole so that none of the, and it's connected to an axle somewhere. So you can rotate along that axis, right? So the force of the magnetic field is going to create a torque. We're going to rotate up on this side, up out of the page on that side and into the page on that side, and then behind the page and then back out of the page, right? That's what the net torque would be. And then we would get it, and it would keep doing that until you get to the vertical configuration. So at the vertical configuration, this is the circuit on the top stays exactly the same. So at the vertical configuration, and I'm trying my best to draw this properly. At the vertical configuration, one of two things could happen. And probably the best thing is that we actually lose contact with the two leads. So maybe the actual current stops flowing when we're in the vertical configuration. I'll do it in the same color. So when we're vertical, we just see, the top, we just see this, and then we see, it pops out a little bit, and then we see this arm right there. and then we see that pole that's maybe holding it or that it's helping it rotate. Right? But we're still having some, the current has ceased, so there's not going to be any torque, no force through the magnetic field because we've lost touch at that point. Right? Because these things kind of point out. Hopefully you kind of, you could visualize how to build such a thing. And we're still rotating in this direction because of some type of rotational inertia. Then, this is what the interesting part is. What happens when we rotate more than 90 degrees? And I just realized that I'm pushing over 10 minutes, so you can think about that a little bit while I stop here and continue this in the next video. See you soon.